All right, looks like we got most folks. Well, good morning, everybody. Once again, I'm Corey Oakley, and I'm the host this month for our monthly series of seminars. And today we've invited Aaron Bunch. Aaron Bunch just finished his PhD at Clemson University. He's kind of been all over the place in the fish world. He used to work for us in a couple of different roles. Aaron, probably 20 years ago, almost 20 years ago, 19, 18, 17, something, I don't know. Anyway, it's been a while.
Yeah, it's been a little
But
bit.
he's also worked in Virginia. He's worked in Arizona. I think he's worked down in Florida. So he's kind of been all over the place. But today he's going to talk to us about anadromous fish and fish passage on the Cape Fear River. So, Aaron, it's yours.
All right, Corey. Thank you so much for inviting me and Heather Evans for putting this all together. I appreciate everybody taking the time out of their busy schedules. I know we're all busy. All right. Make sure I get this going. Okay. Well, just in general, aside from a kind of a hiatus in the Grand Canyon for 4 or 5 years, I've spent most of my career working on something that I put together, kind of this overarching theme with my research, which is complex interactions exist between fish species and their physical and chemical habitats in coastal systems. And fish passage definitely falls under this when I talk about the physical habitat. Now, I worked with Dr. Troy Farmer at Clemson. One of the best experiences that I've had in the profession is working with Dr. Farmer. And we evaluated novel approaches for improving anadromous fish passage in coastal rivers, but this is specifically for the Cape Fear. Now, this is as much a story about collaboration as it is as much as it is about the science. We were working with over 16 organizations and 60 plus people were involved in some form. And I'd like to point out all the people from NCWRC that were integral in this. And I'd also like to recognize Dr. Heather Evans, who is on my committee, who is integral in specifically the eDNA portion of this work. Now, in general, worldwide, river fragmentation impacts migratory fish. You can see kind of globally, I like thinking about things in different spatial scales. So if you think global, um, from Grill et al. 2019 in a Nature article, only 37% of the world's rivers flow freely more than 1,000 kilometers. That's kind of an amazing statistic. And it's mostly those blue lines up there is like the least inhabited portions of the world. So you can see where there's high human density, there's generally high fragmentation. Okay. And there's over 90,000 in the US alone. And then on it, like 90% average decline of migratory fish since 1970, as defined with the within CMS listed migratory fish. So it's very problematic for fish species. Okay, when we look specifically on the Cape Fear River in North Carolina, USA, there are three lock and dam structures, which I'll talk to more individually about in a minute. And beginning in the early 1900s, they were used for shipping goods to upstream cities. Currently, these low head dams are considered low use, but they still function to pull water for municipal withdrawals, at least in a couple of locations. But you can see these different anadromous fish species that have the designations of overfished, depleted, endangered. And when you see those words to describe a fish or fishery, you can tell it's in pretty bad shape. And so here are the locations of the lock and dams within the Cape Fear watershed, LD1, LD2, and LD3, on up to Lake Jordan, and then you'll see the confluence of the Deep and the Haw rivers that come together to join to create the Cape Fear. And then somewhere in, you see that little teeny Smiley Falls triangle up to Buckhorn Dam, maybe up into the Deep and Haw, where the putative spawning grounds for these diadromous fish or anadromous fish that went upstream to spawn. Okay. I'm going to start moving a little bit faster. But adaptive management has been key in this system to try to reduce impact. And maybe we didn't call it adaptive management back in 1962, but we were doing that. And from 62 to 2012, there were various iterations of trying to pass fish upriver. There was the WRC took an important step in the 1960s to say, why don't we have some specific lockages, which I'll show here in a minute exactly what that means. Why don't we have some specific lockages that allow fish to pass these? Because usually they would pass during high boat traffic, but when boat traffic started to wane, there was not as many openings of the locks and dams, and thus those fish didn't really have any where to go unless the water inundated the dam. And that's something we'll talk about as well. From 13 to 21, in 2013, there was a Nature Lake Fishway that was constructed at Lock and Dam 1, but there was only Lock and Dam 2 and Lock and Dam 3 had the lockage. Continuing in 2022. There was a modification to that fishway. There was actually no Lock and Dam 2 or Lock and Dam 3 lockage occurring because of mechanical problems within those structures. But with the Sustainable Rivers Program, with TNC, the Nature Conservancy, and the Army Corps of Engineers, they put together a plan to try to pass fish using environmental flows. Okay, but what I'm going to talk about today is kind of what's happening on the right side of this plot from 13 to 23. And the reason why I can use data going back to 2013 is because it's very generous of Josh Raby to share the data that he and Dr. Hightower put together in the modeling framework that I'm using. But we wanted to kind of understand some key questions within the system. So how do migratory fish navigate the fishway at Lock and Dam 1? So that's one key question. So how do they do it? And where do they do it? And when do they do it? But that's a key to kind of understand and evaluate the structure itself and the effectiveness of the, or lack of effectiveness of a structure. And then our second question was, how do mitigation strategies and flow regimes compare in reducing that impact? So the three different mitigation strategies I just discussed, how does flow play into that? And then how does that help with these migratory fish being able to move upstream? Okay, this doesn't get at, all this is, we're trying to figure out fish moving upstream, but there's a myriad of other issues once fish actually move upstream. Do they spawn? Can they spawn? Do their eggs and larvae actually survive? Is the water too polluted in that area for the fish to develop? There's a whole lot of questions beyond this, but the first step is to get fish to move upstream. All right, very quickly, and this, I give all the credit to Jeremy McCargo for this this particular paper in this chapter within my dissertation, because we're having to use two different tag types. You'll understand here in a minute why. But we use two different tag types. Generally in the literature, there was only one tag type used, and it was a 69 kilohertz Vimco tag that would be pressed into the to the stomach of the shad. These are fish that will die after spawning, just like salmon. At least majority of them in the system do. So that was a quick, easy surgical implantation that we could do to track these fish. But nobody had ever used two different tags. So one of our tags was to get fine scale movements around Lock and Dam 1, that key question, that first question. And then the second tag, which is more the typical tag in the literature, was to understand that broad scale movement and how these fish moved longitudinally up and down the river and whether they passed or not. So ultimately what it came down to is to reduce mortality risk, which is what our tank study at Bears Bluff National Fish Hatchery, that's what we were trying to understand, is that We used a revised tagging method. Instead of holding the fish straight up and pressing the tag vertically down into the fish's stomach with a wooden dowel or a pencil, which is typically what's been used in the past. We made this little device, as you can see, and we also put the fish on its side. It seemed to be a little bit gentler. We also used a non-toxic water-soluble lubricant, either aloe or glycerin, and that was the best option. So we had to kind of figure out our tagging methods first to try to reduce mortality at the most we could, so that in itself would not impact our study. All right, so that plays into how do migratory fish navigate the fishway. And we had this really great collaboration team between NCWRC, NC State, DMF, and especially UNCW with Dr. Fred Scharf. And Kyle Rachels in April were huge with this. And then again, NC State was able to just share the data that they collected from previous years. And so overall, there was boat electrofishing, angling, or gill netting, depending on the target species. You can only use gill nets for sturgeon, and it's very specific water temps and permitting requirements for that particular species. But for shad and striped bass, mostly electrofishing and angling. You may recognize Dion, who's recently addition to the crew, Maggie, who's recent addition, and also Mason. So 3 WRC staff on this one slide. Pretty cool stuff. Okay, so when you talk about fine scale movements, this is what I'm talking about. So on the left, you'll see the plot. This is above and below the Nature Lake Fishway. We cannot put not transmitters. We couldn't put receivers in the middle because of the acoustic noise. They just would not detect the tag, but we could do so. We found out after some pilot work that we could do that, and we had a good understanding of the distance that was needed between these receivers, both upstream and downstream. Okay. And then effectively, to get these triangulated 2D positions, both above and below, like you see on the right-hand side, it's almost like, and this is what I would tell, this is a science communication seminar, so I'll give a little science communication info because I work with the Southern Division, and we put on workshops with science communication. Well, one of the things I talked to the public about was, hey, it's like we put cell towers down in the water and we handed the fish a smartphone, and then it's like we use GPS or triangulation to find their specific location. So it's like Google Maps. That really resonated with people. So that's what we did essentially. And you can see the fish's track on the right-hand side. All right. Well, some different patterns emerged from this fine scale spatial analysis. So we're interested in space use within the vicinity of the fishway. We acknowledge that there are many ways to quantify space. However, we chose to estimate space use via a kernel utilization distribution in an R package, showing where they spent 50% of their time with we call this their core use area. KUD is kernel utilization distribution. In their general use, we define this dotted line around the edge. And this pattern was specific to Atlantic sturgeon within the system. Okay, I'll come back to that. We looked at the different routes. So we have a left route, which is the green. We have a pink or red route, which is the middle. And we have a blue route, which is off to the right. And in this example, this particular fish was an American shad, and it spent most of its time up and around in this corner. There's a sandbar there. And oftentimes these fish would make circular patterns. This is a daily pattern right here. This is one day. Okay. And The blue is when fish were going away from the dam, and the red were when they're going towards the dam. So you can kind of see the differentiation in movements. And this fish, when it decided to pass, it spent most of its time off to river right looking upstream. When you're talking about a river, you always have to give orientation to the river so people understand what you're talking about. So river right when you're looking upstream, not when you're flowing downstream. This fish spent most of its time. Well, then it decided, okay, well, I like the conditions on the left-hand side, and so I'm going to pass, and you can see its track. And it didn't spend nearly the amount of time in the upstream array as it did the downstream. And that was a general result that we found. So if you look at this, again, we don't have data within that gray area because that's the fishway itself, but we can show where the fish entered and when they exited the fishway. And the plots on the bottom are, the numbers that you see are the numbers that entered from one, and then up top is where they exited. So let's see, let's go over here to the right and look at striped bass. There was 9 total fish that passed in 2022. 5 of which made it up to the left-hand side when they started in the right-hand side. And so we can see that 60% passed through that left route. And if you look on the left, we don't have good flow data, but we can see, cursory look at the overhead imagery and some flow models that were run prior to the construction of the dam or the fishway, is that a large portion of the water a larger proportion of the water would actually flow on that side, so creating a higher attraction flow. And if you look in the literature and fish passage literature, that is a major component is the attraction flow, and we think that fish followed this attraction flow. All right. So flow also influenced space use patterns. So you see Orientu on the left is the original fishway, on the right is the modified fishway. And I categorized positioning data prior to the kernel density estimation occurring according to the cubic feet per second data, or the flow or discharge at the gauge, which was located directly at the site. Okay. Every data point was paired with a precise flow rate based on the flow data from USGS. And then I bend all of the positions with that particular group of flows, and then estimated the kernel utilization for both the 50% and 95%, like I explained earlier. And so you can see the original design shows overlap with all CFS polygons. This is specific to shad, by the way. The original design shows overlap with all flow polygons. However, you can see a greater spread of space use following that modification. And what you'll notice just by these, I didn't go into incredible detail about the original fishway design versus the modified fishway design, but the original design, a lot of the water was kind of funneled towards the middle. With this modified design, they created 3 distinct pathways within the fishway. And it seems like that modified fish behavior as well and distributed those fish more below the fishway, which was very likely associated with the changing flow fields based on those pathways, right? So you have a distributed flows coming from the fishway, and in turn we had distributed fish distribution patterns. So pretty cool stuff. And this all ties back to how fish use the fishway, or the vicinity within the fishway. And what you can see is that let's look at fish at greater than 15,000, which would be this pink on the right hand side. And you can see that when it hit 15,000 CFS, most of these fish stayed right to that river left side, just below the gates. And this probably had a lot to do with flow refuging behaviors and trying to maintain their energetics for their continued migration upstream. All right. Now, striped bass also showed a more dispersed pattern of core space use following the modification to the fishway. But you don't see as much distinction between different CFS levels. Okay. In terms of sturgeon, flow didn't really influence sturgeon space use patterns. However, we didn't have as strong of a gradient in those patterns during the time that sturgeon were in the river. It never went above 10,000 CFS. So all you see there are the two lower categories of CFS. But you can see they are utilizing that area for the most part right in front of that pier. And there's a nice deep hole, 30 to 40 feet, depending on flow, that shows where those fish are located. It's nice, clean, sandy substrate. So that's very likely where they're spawning. Okay. So we have spatial habitat partitioning among species. So this is all in 2022 to make direct comparison between all three species, because we didn't have any tag sturgeon that went up into the array during 2021. But what you can see is even in this relatively small area, I'm talking about like probably maybe 3/4 the size of a football field, maybe, probably not that wide either. We're talking about these fish that are like separating themselves, distributing themselves, and likely doing different things. So what's also very interesting and confirms that sturgeon are spawning in this area is that UNCW PhD student Jake Matthews and then Dr. Fred Scharf confirmed spawning. They placed egg mats, which was informed by these data. And lo and behold, they found 2 sturgeon eggs just below that area. So it's confirmed that the area is being used for spawning. And what are the shad and striped bass doing? It's probably a combination of spawning if they don't feel like they can pass, or they don't have the motivation to pass. For spawning, it could be for feeding. We noticed some patterns in striped bass, some daily patterns in striped bass along that left, kind of that left middle area, kind of this green blob at the top is likely a foraging striped bass. And then there's refuging and staging behaviors for both of those species as well. All right, well, let's think about the temporal differences in passage between species. We did not see any passage with sturgeon, so they're not there. But these are individual shad and striped bass that passed in 2022. So you can look at the temporal aspect of this. So we can see the ascent timing. All right, so the start of the line is when they it's basically the last point that we were able to detect them in the lower array. And then the length of the line is the amount of time they spent in the fishway before they popped out on the upper end. And that date and time stamp at the upper end is based on the first detection that we found in that upper array area. Okay. And you can see that it shows the ascent timing and the duration of time it took for fish to pass through the fishway. And generally, what we found was that shad passed more in the afternoon, evening, and striped bass, or more so in the morning. This has important management implications if we're talking about the timing that conservation lockage needs to occur. So let's say the Army Corps of Engineers were mostly locking from like 10 to 11. Well, they might miss a ton of fish because it was not necessarily the time that these species were passing. So, all right. So now let's think about our other key question. And I'm going to talk about a pretty complex model, but I'm not going to really go into the full details. It's a Bayesian model, but don't let that scare you. I want you to only focus on like the probabilities and the patterns that emerge. Don't get don't get worried about all the minutia that goes into the model. Okay, how do mitigation strategies and flow regimes compare to reducing impact? Okay, so we have this large telemetry collaborative network. This was for the 69 kilohertz tags, if anybody knows about acoustic telemetry. The other tags we were using, I failed to mention, are fine scale tags called HTI 495 series tags. But these are the more of the standard kind of longitudinal broad scale tags, right, from Innovacy. All right, and there's Jake with some of the sturgeon sampling. All right, so I used a multi-state model in the Bayesian framework. This is a Cormack-Jolly-Sieber mark recapture model. And here I focused on the transition probabilities or movement probabilities. We're going to define them as movement probabilities. And we're defining those as the probability of an individual fish moving within a specific time step. Whether the time step was 1 day or 3 days, it's the probability of that fish coming in contact with one of the locking dams and whether that fish passed or not. Okay, which is different than passage efficiency. Passage efficiency is more of a long-term hit, the number of fish that came in contact with it divided by the number of fish, or excuse me, it's the number of fish that passed divided by the number of fish that came in contact. So passage efficiency is different than what we're talking about here. All right. We focused on upstream passage probability for this talk. And we have 2 species only because of striped bass and American shad. We're the only ones that passed, at least with the acoustic work. We'll talk about DNA here in a minute. And we had 5 years, so 2 times 5, we had 10 separate models, and we used a similar approach that we did in some of the Virginia blue catfish work that I worked on. We're very fortunate to work with a high performance computing cluster called Clemson Palmetto, which is a huge resource. So it's a supercomputer that we're able to run these models on. Instead of it taking 3 weeks to run models on my computer, it took about 16 or 17 hours. So that was very beneficial. All right, so here are the geographically defined model states, with each color representing a different model state. The lower river main stem and tributaries below NC 11 bridge was considered model state A. That's the green. So that's a pretty big model, pretty big state, the size of the state. Model B is represented in blue, very small. It's only from Locking Dam 1 down to NC 11. And then the remaining model states were based on river sections between each locking dam, right? And so if you look at this a different way, excuse me, I've got a little bit of a cough going on. You can see that each model state delineated by a different letter has either no impediment or like a temporary, or I call it like maybe a permeable lock and dam situation at LD1 with the Nature Lake Fishway, and then more impermeable at LD2 and 3, and then up at the very tip top, Buckhorn Dam is not passable at all, and there's no fish passage in that area. So that is the very end of the anadromous run in this river. And so again, we're focused on estimating movement between these model states. We're only, for this particular talk, we're only talking about upstream movements. We had different time steps between March 1st and June 30th. So all detections were combined over 3-day periods. And this was also important. And one of the main benefits of this model is that you can incorporate flow as a covariate in this Bayesian framework. And then you can model the probability of fish passage or upstream passage based on a flow that would be happening at that time. Okay, so mean upstream passage probability as a function of the flow covariate. If anybody in the group is a Bayesian statistician, you can see these, there were uninformative priors that we used with different distributions for each parameter. All right. So overall, passage did not improve with the Fishway modification. I'm sure this is not fun to hear from a lot of the people who spent a lot of time and energy to get this Fishway installed and to modify it and really push for adaptive management. It can be disheartening, but the science and the data is telling us that American shad really didn't change. We found a little bit lower, albeit, less than 10% probability for both years is slightly lower striped bass than striped bass overall between the original design and the modified design. Okay. And I've had some discussions with David Smith that the Army Corps, ERDIC is the acronym there. And we kind of thought like, okay, well, it might not as much matter about design with this type of Fishway. It might really, the slope might be really important. So maybe the slope needs to be extended out for these fish to be able to pass more efficiently. However, that's like doubling or tripling the cost, which is why they made the slope the way they did. But that's what the data is showing us. Maggie has an additional year of data, plus there's going to be even another year of data on top of that. So, but we'll see what happens over the not really long term, but this 4 to 5 year data set that we have and how it compares to the Raby data. But when we look at original Nature Lake Fishway natural flows, a lot of that's the Raby data. All right. E-flows. So if you look specifically at E-flows, which is one of the major questions that we had, E-flow alone did not address mitigation needs. Okay, we can't affect the weather. Like we cannot say rain when it needs to rain, right? And there are particular times within the evolutionary, these fish have evolved a certain way of moving upstream, following these environmental cues, and we can't just make it rain. Well, there also has to be a certain threshold that around 17,500 CFS is when these locks and dams will become inundated, okay? And that's when I talk about the E-flows, we have dam submergence flows is what we've termed them. It happens around 17,500 or more. And so what you can see here is at Lock and Dam 2, look at the left plot. And for American shad and striped bass all the way to the left, there's those years where conservation locking occurred and there was natural flows that may have inundated. But then if you look to the right, you can see where the E-flow that was the only option that managers had over the past few years, because the locks and dams were not functional. And the only thing we could do was try to manipulate water from Lake Jordan and store water in Lake Jordan to supplement a natural flow event that would be coming down from mainly the deep. And so there was some prescriptions that occurred and some thresholds that had to be met. And there was a whole lot that had to go on to even attempt one of these flows. But the idea was to try to inundate these dams during peak spawning for these anadromous fish for them to go upstream. Okay, and what you can see is overall we had lower passage probabilities for both fish. at Lock and M2 and Lock and M3 when management was limited. So what does that tell you? It tells you that conservation lockage is probably pretty important in this system. Okay, high flows improved fish passage, right? And it makes sense. The good thing is the model is showing us what is logical. And some models don't do that. Well, this is good that we're able to see what we expected to see. And overall, in most of the modeling scenarios, you have the different locks and dams across different species. And, you know, I'm not going to go into the fine details of this plot, but in general, you see more lines that are increasing than you do are decreasing. And that's what we mean by higher flow improves passage probability. And this flow z-score, this is just a way, like 0 is considered average flow, anything above 0 up to 3, somewhere between like the upper 2s or 3, that's where that dam submergence flows come into play. So you can see that passage really start to increase based on that, especially for striped bass at Lock and M2. Striped bass, when they reach Lock and M2 and there's a big flow pulse, that's when they tend to pass at a higher rate. Okay, what's also interesting is that Maggie, here on the right, these were, I think this is from 2023 data, and you can see that most of the American shad in that year passed just after the peak, which makes sense. So they're using that station holding behavior from the spatial data that I showed, that 2D positioning data that I showed, the space use. And then as soon as the conditions are right, they'll pass. So that's the stuff that she's working up now, which is really cool to see. Going to go through, I think we only have 5 or 10 minutes left. But this was also really fun and important because, like I said, we did not detect. There was you know, 15, 20 individuals that we had tags in, that Fred and his crew, and I jumped on occasionally and tagged Atlantic sturgeon. And we had receivers all up and down the river, just like we did for American shad and striped bass, but none of the tagged fish actually passed. But we thought, okay, well, this is a rare species. You know, we don't have that many tags out. There's going to be a lot of untagged fish out there too. So let's see what happens with eDNA. And so we had ground truth field sites. We had the assay, ground truthing at hatchery at the Bears Bluff National Fish Hatchery. We have river samples for evaluation. Took my daughters out a few times and we collected water. We have sample collections, filtered it, DNA extraction, and then ran qPCR, which is quantitative PCR. And this was with the hard work and dedication of Heather Evans and her crew, Kara, and others at the Museum of Natural Sciences. So that was an important piece of this whole project. And we collected water throughout the migration reach all the way up to Buckhorn Dam. And you can see the different sites in yellow dots. And then you can also see the relative position of the acoustic receivers for detecting tagged individuals. We tried to match with those eDNA sites. All right, well, we also wanted to validate, I guess not validate, Lewis Plow and Maryland and myself and others authored a paper on the Atlantic sturgeon assay that was used in this project as well. And we tested that assay with the hatchery samples and also field samples. We had a really good detection. We had 100% eDNA presence. And then overall detection rates, which is, we ran everything in triplicate. So we had multiple replicates per sample site. So that's why you can see there's different detections associated with that. So it'd be like a 1 out of 3 or a 3 out of 3 You get the gist there. There's no difference in our quick analysis on hatchery versus field. But what you really want to know, and the bulk of this, is that sturgeon eDNA was detected above locking dams. And that was a very, very cool part of this project. You can see up in the left gray box, we did not test those samples. What I did was, for efficiency's sake, this stuff takes so much time and a lot of money. There's a reason why you might not get your data directly back from Heather and her crew, because this stuff takes forever. And you have to be so meticulous and do it correctly. So that gray box, though, is a void, because what we did is we said, okay, we're going to amplify all these sites across all these weeks, 14 weeks in 2022, across 11 different sites up and down the river. And we're going to run qPCR and amplify those up to Lock-in M2. And then once we get a hit at below Lock-in M2, then we'll go above. And that's what we did. Okay. So that's why it's sequential sampling design. And what was cool, we're talking about the replicates. So 1 out of 9, 1 out of 9. These were pretty low probability hits, but hits nonetheless. What's really neat is March 30th, we had fish up and down the river. We had all the way up to Tar Hill boat ramp, which was this 3 out of 9 delineates, so 33% probability. So 3 of our replicates out of 9 total in that area. Really strong below Lock-in M2, 7 out of 9, and then kind of a decreasing pattern on down to Lock-in M1. What was really cool is you can see this downstream at Lock-in M1 site on April the 5th coincides with our spatial data. So we did get some detections of fish, and here are the actual fine scale habitat use polygons that was created based on the fine scale data on that date of collection. So we had, in this particular date, on April the 5th, we had 7 out of 9 eDNA detections. We had 3 fish swimming right in front of the sampling site. That was pretty cool stuff. And a similar pattern was found on April 19th. Okay, Corey, I'm about to finish up. Here's also important, because you can see the first detection after the peak yields positive eDNA detection. So there was a putative passage window for sturgeon to pass when we found the eDNA. And during that time, we had an E-flow, and then also a large natural event right just following that E-flow. So we did see at least sturgeon DNA, likely based on those high flows during the previous week or two. So that was pretty awesome. Also, Brandon Peoples and Colby Dennison at Clemson did some work in the PD, and they show different cues to migration. And what you see on the bottom plot is based on their data. And we show our first detection and last detection based on their cues. So we're able to match what's occurring in the PD with our first detection in the Cape Fear with eDNA and our last detection, which was pretty neat. All right, so kind of just putting everything together. So we have this big overarching theme that I've worked on. Complex interactions exist between species and their physical and chemical habitats and coastal systems. And then we understand that river fragmentation impacts migratory fish. And that adaptive management has been used on the Cape Fear River to reduce impact. Reduction of impact is the key. There's still lots of impact. And then we try to tackle these 2 questions with the different methods, a pretty diverse set of methods. multiple telemetry systems, eDNA, different modeling structures, trying to incorporate flow. That's the innovation that we've talked about with this project. But then there's all these age-old problems that have been going on since, the start of the whole situation. And conservation lockage and some of these questions that have been around for a long time, which we've tried to tackle those with more novel technology. And overall, what we found, fish followed attraction flow at the fishway. This shouldn't be surprising if you know anything about fish passage literature. But what surprised me is how spatially, separated these fish were within a relatively small area. That was pretty impressive. What we'd love to have is a big flow model just below and all these depth contours. And we don't have that, unfortunately, at least in our hands right now. There was some work done. We're trying to get our hands on this data to try to overlay that information on top of our fish movements. And then you can see there's temporal differences in passage between species, and this may have some important implications for when conservation lockage should occur. Okay, so how does mitigation strategies and flow regimes compare? Well, passage did not improve with fishway modification, at least with the data that I have in my fingertips. E-flow alone did not address mitigation needs. There needs to be many tools in the toolbox used in this system. There is not a one size fits all scenario. There's not a silver bullet. You have to use every type of management strategy that you can think of to get these fish upstream. And then what happens to those fish when they get upstream? Are they actually spawning? Are the offspring surviving? Those are additional questions that need to be answered. And then we also show that high flow improved fish passage. But one of the key things that I talked about early on is that this could not have been achieved without a strong collaborative network of NCWRC personnel, Clemson, UNCW, NC State, all of these people, DMF, all of these folks, Army Corps of Engineers, allowing us to access these systems. But it took a lot of people to do this amount of work. Okay, I think that'll do it for today's seminar. I'd love to have any questions. Hopefully I can answer them.
All right, thank you, Aaron. As always, folks, you can type the questions in the chat. I'll give just a couple minutes. We are running a little bit long today, but I'll give a couple minutes to anybody who wants to put a question in the chat.
Yeah, and I'll also say if you need to email me or discuss anything beyond this, my email is going to stay the same for a while and then it'll change. But for now, it's ajbunch@clemson.edu. So if you have any questions at all after this, you can also email me or call me, whatever. Corey knows how to get a hold of me. Get a hold of Corey and then we can work it out.
Don't get a hold of me. No. Aaron, I put your email in the chat. Make sure that's right.
Yep, that's it. Yeah, long way from a green temp employee at Armstrong. That's funny.
It's been a long time ago.
That was 2003.
All right. I don't see any questions rolling in, so we will conclude today's seminar. Thank you, Aaron, once again for being here. Really appreciate your time. And we'll see all of you next month. Thank you.
All right. Thank y'all. See ya.